you can see that loop quantum gravity is even investigated in China. I met Yongge Ma in Penn State when he was visiting. Actually, you were not a postdoc, right? You were visiting professor.
It's a postdoc.
I see. So Yongge was a scholar, postdoc in Penn State, and I was very impressed by operators he defined in framework of loop quantum gravity. And since then we continue, and actually our collaboration is more and more intense with time. The title of Yongge's talk is Isolated Horizon Entropy in Loop Quantum Gravity.
Okay, thanks Jurek for the introduction, and in fact I'm honored with Jurek as my collaborator and friend, and in this occasion of the 60th birthday of Jurek, so I'm happy to deliver a talk and for his birthday. So in this talk, I will first give a very brief introduction to the isolated horizon notion and some basic elements of loop quantum gravity. And then I will introduce the so-called Chern-Simons theory description of isolated horizon entropy in loop quantum gravity. And then I will introduce another approach, namely the so-called BF theory description of isolated horizon entropy. Then I give some concluding remark. So we know that the notion of event horizon in GR is a global notion, but this global notion requires knowledge of the entire space-time all the way to the no infinity. So also, if we are in the usual treatment of black hole thermodynamics, one would need a stationary space-time for including this event horizon. This is not ideal because somehow in many astrophysics case, we have black hole, but outside the black hole there are some other radiation, but the black hole itself is static. And so from another viewpoint, if we want to use quantum gravity to account for this black hole issue, then the global nature of event horizon makes it difficult to use quantum gravity. Because in order for a definition of a horizon to make sense, we need to be able to formulate this notion in terms of phase space functions, which can be quantized. And these phase space functions usually is locally functions. And the global notion of, we know the ADM energy and ADM angular momentum also have limit use because they do not distinguish the mass of black hole from the energy of surrounding gravitational radiation, something like this. So this motivates around this year, Abai and his collaborators proposed the notion of isolated horizon. This is defined quasi-locally as a portion of event horizon which is in equilibrium. For example, you may have the horizon in this part is in equilibrium, but the other part may have radiation, or may have some matter, even some matter field fall into the black hole. Also, here is in equilibrium, but here is not. Here is in equilibrium. So the isolated horizon is just referred to this portion which is in equilibrium. So the exact mathematical definition we can for this isolated horizon looks like this way. We have a three-dimensional no hypersurface of a space-time, and this spacetime, this hypersurface is called isolated horizon if the following four conditions are satisfied. So this hypersurface should topological R cross two-dimensional compact manifold, and the expansion of any non-normal to this horizon, to this three-dimensional null surface vanishes. And this means it's non-expansion. And also the field equation hold at this horizon, and some reasonable energy condition are satisfied. We also, because there is a degrees freedom here to choose this non-normal, we just choose one equivalence class that they are equivalent if they just different by a constant. Then this class, any one of this class will satisfy the condition that this the connection restricted to this horizon will be redirected by this this normal. So this condition is essential in order to have the zero law of this horizon. Then, as far as I know, Jurek is the first one to find non-trivial solutions to Einstein equation that including isolated horizon, and are surrounded by some radiations or some other. It's not the global black hole solution of Einstein equation. And I said that because this fourth condition of isolated horizon, the zero law of isolated horizon mechanics are satisfied. Namely, this surface gravity defined by this formula is a constant on the horizon. So, in this case, if one consider a four-dimensional space-time region with isolated horizon as an inner boundary, you can discuss the Hamiltonian framework for this region with internal boundary. Then this Hamiltonian framework provides an elegant way to define the quasi-local notion of energy and angular momentum associated with isolated horizon. So in this case, one found the first law of isolated mechanics, horizon mechanics holds with these quasi-local quantities, like the energy and the area, and this is just the standard first law of usually black hole thermodynamics. Okay, so this is the framework of isolated horizon. And I think yesterday there are good, excellent talks by Hanno and Christine about this. There is a unique gauge and diffeomorphic invariant cyclic representation of the holonomic flux algebra, which is given by the so-called Aztec Lewandowski measure. This is lowest theorem. Then, in fact, in the Kinematical Hilbert space given by this representation, there is a basis called spin-network states, or it consists of spin-network states. This spin-network states is defined over some graphs in the spatial manifold, and this graph, on each edge of the graph, there is a spin representation of SO2, and in the vertex of the graph, there are intertwiner between these representations. So then, I think the idea was first raised by Carl very early, that we can in fact use the area operator, the spectrum of area operator in loop quantum gravity, and to consider the entropy of black hole horizon. So if in the case you consider the spatial manifold has a boundary as a horizon, then you can think some edges of spin networks in the bark will interact with this boundary and indulge it a quantum area at its interaction. So for a given area, and people would be able to calculate the micro degrees freedom that contribute to this area. And this idea was then generalized by Abai and its collaborators to consider this boundary as the isolated horizon. So if we consider the Palatini action of general relativity on the space manifold with an internal boundary, then the action looks like this way. And we find that we need a boundary term for infinity, but we do not need a boundary term for the internal boundary because of the isolated horizon condition. Now, this E is just the co-tetrad, and A is the Lorentz connection, and this is the curvature of Lorentz connection. And we also overly use this solder form. Is just the wedge of the two of the co-tetrad. Then you will find that the second order variation of this Palatini action leads to the conversation identity of symplectic current. I mean, we want to use to get some symplectic structure by the covariant phase space approach. Then we do this second order variation, and we find this formula. So in this case, you will find that the symplectic structure of the bark can be read from this because it's M1 and M2 is just the spatial manifold cut this space-time region. And also we get a formula for the horizon, isolated horizon. Then you will find that the symplectic flux across this horizon can be expressed as a sum of two terms. It's corresponding to the 2D compact surface is the interaction of the horizon with these two spatial slices. Now you can find that if we use the time gauge, which was usually used in the Hamiltonian analysis of the connection formalism of GR, then you will find that this Lorentz connection and also this tetrad can be somehow gauge fixed. Means we use time gauge that is the zero vector of this tetrad is normal to the partial Cauchy surface of M. Then this will reduce the internal local gauge group from Lorentz group to this SO3 group. Or if you like, we can extend it into SU2 group. Then the pullback of the spatial variables to this spatial hypersurface can be written in terms of the so-called Aztec Barbara variables. So this gamma is the Barbara image parameter, and we also introduced the notion of this E, which is just the spatial Lewandowski simple contract with this sigma. This Ij is from 1 to 3, while the capital Ij is from 0 to 4, from 0 to 3. So in this case, if you consider, for example, the spherical symmetric case, with spherical symmetric isolated horizon and with a given area, then you will find that the symplectic structure can be obtained on this spatial manifold with the internal boundary, the intersection of it with horizon, and you will find that the symplectic structure takes this formula. So, in fact, this is the standard symplectic structure for connection formalism of GR in the bark. And this is the symplectic structure of SU2 Chern-Simons theory on the horizon. Then in terms of this Aztec Barbara variables, you will find that the isolated horizon boundary condition will take this formula. So this is the curvature of this Chern-Simons connection, and this is the area for the given area, and this is the Barbara image parameter, and this is the sigma is just the components of this Sauter form. It's related to the Chern. Okay, so in this case, we already found that we can use the SU2 Chern-Simons theory on the boundary to describe this boundary degrees of freedom. Then we still have some choices. These choices is the gauge group for this Chern-Simons theory. What I introduced in last page is about this SU2 Chern-Simons theory. Well, previously, people would like to use this U1 Chern-Simons theory. So, and it was so that this U1 Chern-Simons theory approach, then it applicable to arbitrary axial symmetric isolated horizon. But as far as I know, currently, the SU2 group approach of Chern-Simons theory is only applicable to spherical symmetric isolated horizon. Anyway, with either possible choice, because this U1 group somehow comes from gauge fixing, you fix some internal vector so that this is contraction with this density chart will normal to this horizon somehow. Use this condition to fix the internal gauge group. Then with either of these choices, you can use a detailed analysis to estimate the number of surface Chern-Simons states on the punctured horizon consistent with the given area. So for the state counting, one usually use the spectrum of standard area operator in loop quantum variety. We know this is very useful formula for the area spectrum, and this area spectrum is valid for the case that there is this edge of spin network intersect with one point, with an endpoint or inner point with the two surface. Then, by this standard area operator, one can find that the leading order expression of the entropy agrees with Beck-Hawking formula by choosing a particular value of this Barbara image parameter. So it doesn't matter if you choose this U1 group as the structure group of Chern-Simons theory or SU2 as the structure group. And you can also even calculate some quantum correction for the entropy. Then the subleading order expression of the entropy are log terms. It's also for either case it's a log term, but the front coefficients of this log term are different. So if you choose U1 group, you will find this value as the coefficients. But if you choose SU2 group, it's this value as the coefficient. So there are, in fact, alternative suggestions. This alternative suggestion is that we can use, instead of standard area operator in loop quantum variety, we use a so-called flux area operator for isolated horizon. This flux area operator somehow come from, we use that internal vector to somehow choose flux. This flux is the integration of this density chart that orthonormal to this two surface. Then you will find classically the result is the same as the classical area of the horizon. So then you get this spectrum of this flux area operator. This is just a sum over the interactions, and at each interaction is the magnetic number on the edge, on the edge. But with this choice of flux area operator, there are some problem. This problem is that the Barber image parameter will take different values for different cases of horizon. Namely, the horizon area, if it light in terms of the smallest area in terms of this Planck area multiply some number, then you'll find that the value can be even or odd. But for this even and odd case, this Barber image parameter has to take different values in order to coincide with the result of Hawking and Bekenstein. Also, we found that this above isolated horizon framework can be generalized to arbitrary even-dimensional spacetimes. In this case, the horizon degrees freedom are encoded in the so-called SO2n Chern-Simons theory. This 2n equal to the dimension of spacetime. So we see that there are some limitations. The limitations is that this Chern-Simons theory description of isolated horizon requires that the area of the horizon has to be fixed. In order to derive this Chern-Simons symplectic structure, you ask this area of horizon is fixed at the beginning. And the other limitation is that the framework is only valid for even-dimensional spacetime, because we know that Chern-Simons theory can only live on odd-dimensional manifold. So with even spacetime, the no hypersurface is odd dimension. So then you may ask, is there any way out to overcome these limitations? Then this approach is in fact the so-called BF theory approach. So the early work on this is we found that we can use the so-called SO11 BF theory to describe the degrees freedom of isolated horizon. And also there are nice work by Hanno and his collaborator, and one can even use some SU2 BF theory description of this spherical symmetric case isolated horizon. Okay, now we think this approach. So in fact, we found that in the calculation, actually, it's very useful for Jurek's coordinates. This is that in the neighborhood of horizon, isolated horizon, we can choose this so-called boundary-like coordinates. The boundary-like coordinates is something this r equals 0 characterize the horizon, and we have a v is just the parameter of the non-normal of the horizon, and the exact I is this coordinate in the two spatial slices of this horizon. Then we also near the isolated horizon, it is convenient to employ the Newman-Penrose formalism, that with this no tetrad, and to adapt it to the horizon, such that this this is the non-normal, and this is the coincide with this is another no vector coincide with the outgoing and the ingoing future directed no vectors at the horizon. And in this adaptation also ask this M, this complex no vector, to be dragged by this normal. Then we need to connect the co-tetrad with this no tetrad. Then we ask that the co-tetrad which are in the coordinate phase space compatible with the metric, they are related to the no natural by this formula. For this formula, we in fact already gauge fixed the two and the second and the third covector of the cotetrad, but the 0 and the 1, they are still leave some degrees freedom of changes. Namely, we still have we can do some boost in the plane formed by this two cotetrad, two covector of the cotetrad. Then we can again consider the Palatini action defined over this spatial this space manifold with internal boundary, and again use the coordinate phase space to study its symplectic current. Then we find that in the horizon, the current is reduced to only these components in this formula. And also this sigma 2-3 components of this solder form, it is closed. Then we can always define one form locally on the horizon such that this sigma is just a dB. So if you take the SO11 boost, that we leave the freedom when we related the cotetrad to no tetrad, then we find that this components of 0, 1 of this connection transforms as a SO11 connection. And this sigma is in adjoint represented. So if we express them in terms of Aztec-Barbara variables, then the full symplectic structure can be obtained as this way. This is still the standard symplectic structure for Bach connection formalism. And on the horizon, we in fact get symplectic structure of so-called BF theory. It's one form and is in the adjoint representation and as a 1-1 connection. So then if we adapt the structure of loop punctuation in the Bach to adapt this, the boundary BF theory is interacted by spin networks, and it should satisfy these equations. Namely, this curvature of the connection is always 0, but this B is equal to this component of solder form, is dB. So then we assume that the graph underlying a spin network state interact the horizon by n interactions. We denoted as this way, and for every intersection, we associate a small enough bounded neighborhood. Then the physical degrees freedom of our source BF theory are just encoded in these variables. This small enough is only consider one interaction, only contains. Then we obtain the quantum Hilbert space of this so-called BF theory, but it is in fact with n interactions because all the degrees freedom come from these interactions. So it's just look like n particle in 2+1 space-time. So then we consider the Bach Kinematical Hilbert space depend on this graph with the set of endpoints on horizon, and this we use this Bach Hilbert space can be spanned by the spin network states with some endpoint on the horizon. So this J is just the spin number on the edge, and the M are the magnetic number of the edge. Then we find that the integral can be promoted as an operator. We integral this sigma 1, it's a component of solid form. Then we got this formula. This is the, we can derive its action on this spin network states. Also because of the horizon is topologically compact, and this imposes additional global constraint on this magnetic number. The sum of this magnetic number over all the interaction points in the section point should be equal to 0. Then we find the equation of this boundary BF theory will motivate us to input this quantum version of horizon boundary condition. This horizon boundary condition we impose it on the Hilbert space of the tensor product between the horizon BF theory and this Bach LQG. So this is in fact ask they should equal to each other. This classical formula is valid for in quantum case. Then to solve this equation, you will find that the space of canonical state on a fixed graph should satisfy the boundary condition and can be written in this way. And this means that this boundary Hilbert space, the number on its interaction should equal to the magnetic number of this spin network states. Then the imposition of diffeomorphism constraint also implies that we only need to consider the number of interactions of the spin network with horizon, but the positions of interaction are irrelevant. In this case, we would like to employ this flux area operator proposed by Jurek and his collaborator. And because in this case, we can easily impose the area constraint as an equality. Namely, it's just this absolute value, sum of the absolute values of the magnetic number on each interaction point equal to the area. We already subdivided this area by this unit. Then we find that for a given horizon area, the horizon states satisfied boundary conditions are labeled by the sequence. We can use to multiply this mi to be, so that we get some integral. Then we can assume that each given ordering sequence, there is at least one state in the Bach space which is analyzed by the Hamiltonian constraint, then so that we can trace out the Bach degree field to give boundary degree field. Then in fact, there are very powerful techniques proposed by Barbara, Jurek, and Villaseno, and that by the so-called generating function method. Then we find that the dimension of the horizon Hilbert space compatible with a given horizon area will just equal to the coefficients of the term, which is say to 0 or x to 2a in the expansion of this generating function. Then use this, we can actually get the entropy for such an isolated horizon. This is given by this formula. Then we find if we fix the Barbara engine parameter to this number, and in fact this number coincides with its value for the even value of the, if the 2a equal, as an even number of the flux area in Chern theory, it coincides with that case. And we will find that the Bigginson-Hawking area law can be obtained. Also, the quantum correction to this Bigginson-Hawking area law, in our case, is also a log term with these coefficients. So this coincides with its value in the U1 Chern theory approach. And also we have some constant. This constant is very small comparing to this log term. So we can also, if we like, we can also employ the spectrum of standard area operator for the state counting. In this case, the entropy formula would again similar to that of U1 Chern-Simons theory. Actually, this BF theory approach has the virtue that it admits extension to arbitrary dimensional horizon. And in this case, for higher dimensional LQG, people would use this SOD connection. D is the dimension of space-time. Then we found that in order to coincide with the semi-classical expression of black hole entropy, again, the value of this bubble impedance is fixed as this number, but this number is half of the number if we use in the 4D case that we use this SU2 connection as the back connection. So let's summarize that this quasi-local notion of isolated horizon lays down a suitable framework to study black hole entropy. This loop quantum gravity provides a fundamental scenario to account for the static origin of the isolated horizon entropy. In the Chern-Simons theory description, the boundary degrees freedom are encoded in Chern-Simons connection, while in the BF theory description, its connection becomes pure gates, and the non-trivial degrees freedom of the horizon are encoded in this so-called B field. And the entropy formula of isolated horizon derived from this BF theory coincides with one case, with the case that the area divided by some smallest area will become an even number. Coincide with that case. Coincide the leading term as well as this sub-leading term. So then it indicates the same value of Barbary parameter and the same coefficients of sub-leading log term. In the BF theory approach, the area of horizon is not fixed, as we said. When we do the derivation, we did not fix its area. So this area is encoded in a dynamical variable B field. So such that this covariant phase space of the system is enlarged so that all the space-time solutions with any isolated horizons as the internal boundaries are included. And the BF theory expansion of horizon entropy is applicable to general isolated horizon in arbitrary dimensions. Also, in this generalization to arbitrary dimensional space-time, based on this SOD connection, the value for this Barbary parameter is dimensionally independent, provided you use this connection. In 4D case, the different choice of connection formalism imply different value for Barbary parameter, because in 4D case, we can use either the Aztec-Barbara connection or with Bodendorfer, Tiemann, Chern connection. In this provides the possibility to determine the internal gate group of LQG from other considerations, because they give different values Barbary parameter. In other considerations, maybe can check which one is consistent. And also in our current entropy calculation, we calculate the dimension of the horizon hyperspace with a given horizon area. So this treatment is essentially only consider spherical symmetry isolated horizon, because only for spherical case, you given area, the horizon is given. So to further consider more general case, we would need to introduce notion of multiple momentum of isolated horizon, and this related work are still being studied. So that's all. Happy birthday to Jurek.
Thank you. Actually, you may notice that this is the full version of the of the photo which you have on the poster, which also includes the environment. That it was taken in Forbidden City, so it's not fake; it's real. Okay. Questions and comments, Carlo?
This value of gamma 2 pi, log root of 3 over 2 pi. It's very interesting. Is that do you have any hint of other other instances with this particular value of gamma could play a role? Is that, it seems to be saying something. Do you have something else to add about the value?
Yeah, perhaps, I mean, in the case of LQC, there are some works by Abba and his collaborator that to coincide with the CMB power spectrum, then somehow this gamma should be in some region, right? But in both cases, I mean, either in the Chern-Simons, either we use the area standard area operator, or we use flux area operator. Both are inside this region. So it's somehow, anyway, it still coincides with other considerations.
Thanks.
Yeah. Okay.
Hanno.
I just want to follow up on Carlos' remark. So very specifically, there was at some point there was some excitement because there was a Barbero-Immirzi parameter that was kind of similar to this. It had a logarithm and it had a pi in it, and somehow you could make some heuristic argument that it has to do with a shift in area from where a j changes from 0 to 1 or something like this. And so my question would be if this gamma is that gamma, or they have anything to do with each other.
Yeah, this gamma is the gamma appear in the spectrum of area operator. Yes.
No, but so there's a specific value of gamma where one could make this connection between quasi-normal mode spectra and LQG, the area spectrum.
Right. As far as I know, in the quasi-normal mode calculation, they will give the gamma somehow coincides with this quasi-normal case if you use Chern-Simons theory, but rather it's the internal group as O3. I mean, for four-dimensional case. Yes. So, but in our case, it is not just the same as that case. But this is true that one maybe need to check whether there are possibility to do this, because this value come from if we use flux area operator.
Yes.
But yeah.
It seems when one has an equally spaced area spectrum, then from
Right. Then Then the detailed consideration may be a little bit different. So that need to check. Thank you.
I have to clarify also some historical facts. So here at this conference, all speakers are very generous as far as giving credit to me is concerned. I don't know why. No idea. But as far as this value of Immirzi-Barbero parameter gamma is concerned, which you showed. Actually, the story was that Ashtekar, Baez, and Krasnov, they formulated a model. Then me and student of mine formulated some combinatorical description of the states which account to entropy. And Krzysztof Meissner, who is here, he was referee of my student's thesis, and he calculated the solution to this combinatorial problem. So we owe him this value. And later, Fernando Barbero came with all theory and showed us how to calculate exactly for all combinatorial problems which may appear for various models. I would like to introduce one more character here. Professor Białynicki-Birula just entered the room. Professor Birula has been the teacher of quantum field theory for many generations of physicists in Poland, and particularly in this physics department. So thank you for coming.